Alright, so let me recall, we are trying to show that every complex torus is actually an algebraic elliptic curve. So let me continue with what I was doing in the previous lecture. So if you recall, we started with tau in the upper half plane, and then of course we had the lattice L of tau, and we also had the torus T sub tau, which is just the complex plane modulo this lattice, and associated with tau is the Weierstrass phi function phi tau of z, and this is this phi function is defined in the in the complement of the lattice on the complex plane, and it is a holomorphic function, and at the points of the lattice it has poles. These are double pole at each of these points of order, that is pole of order 2, and with sum of residues 0, and phi tau satisfies differential equation, first order differential equation, phi prime tau of z whole cube whole squared is equal to 4 times phi tau of z cube minus 3 minus g2 tau phi tau of z minus g3 tau, and in fact what we did was in the last lecture we noticed that this can be treated as a you can look at this as a polynomial in 2 variables. So you so you look at the polynomial y squared is equal to 4 x cube minus g2 tau x minus g3 tau, okay, and then what you do is you look at the locus of zeros of this polynomial in C2. So we look at this locus z2 sub tau, this is a set of all lambda comma mu in C2 C cross C, such that lambda mu satisfy this equation, this polynomial equation, when I plug in for x lambda and y mu, okay. So so what I will do is I will just call, I will define f2 tau xy to be this polynomial, namely 4 x cube minus g2 tau x minus g3 tau minus y squared, and then if lambda mu satisfy this polynomial with lambda substituted for x and mu substituted for y, if and only if lambda mu is a 0 of this polynomial. So I will just write this as f2 tau of lambda comma mu is 0. So this z2 tau is called it is called the affine elliptic curve, affine elliptic algebraic curve associated to tau, okay. So it lives inside this lives inside C2 it lives inside C2, which is C cross C, and what we did yesterday was we proved that you can define a map phi sub 2 so let me make that statement more precisely. So on the complex plane minus the lattice points, from there to C2 there is a you can define the following map: z going to phi tau of z comma phi prime sub tau of z, and I call this map as phi sub 2, and this map is of course invariant under L tau, because phi tau and phi prime tau are invariant under L tau, they are doubly periodic functions, elliptic functions, and therefore this map goes down to a map of the torus minus the point x0, the point x0 being the image of the lattice. All the points of the lattice go to a single point because they form a single orbit, a single equivalence class, and I call that point as x0, and this map is just restriction of the natural projection from the complex plane to the torus. Okay, and this, of course this is an open set, and this is also an open set here. I have just deleted a point, and so what happens is that inside the C2 we have Z2 tau sitting inside this affine algebraic elliptic curve is sitting inside C2, and by definition the map goes into C2 because these two phi and phi prime satisfy this polynomial due to this differential equation, and therefore you get a map which also by abuse of notation I will call it as phi sub 2, and what we proved yesterday was that phi sub 2 is a bijective continuous map. Okay, so let me write that here, is a bijective continuous it's a bijective continuous map. Now what I am planning to do today is I want to tell you more about this map. So I want to explain how there is a natural structure of Riemann surface on Z on this E2 tau, okay, and I will also explain how this map becomes when E2 tau is given that natural Riemann surface structure. I will explain why this map becomes a biholomorphic map. So therefore the aim of this lecture will be to tell you that there is a natural Riemann surface structure on this, there is a natural Riemann surface structure on this such that this map phi2 is actually a biholomorphic map, holomorphic isomorphism. So indeed the upshot of the whole story is that this differential equation that the first order degree 3 differential equation that phi satisfies gives rise to an algebraic equation, a cubic equation, and that cubic equation defines its zero locus in C2 defines an elliptic algebraic curve, and this elliptic algebraic curve is naturally a Riemann surface, and this identification of the torus minus this point, this open subset of the torus with that affine elliptic curve is actually a holomorphic isomorphism. Okay, so that is what I am going to do in this lecture, and let me also tell you what I want to do later on. Later on I will explain how this affine elliptic curve can be compactified by adding a single point at infinity, a so called point at infinity as it is called in algebraic geometry, and then and you can send x0 to that point, and this can be done in such a way so that even after adding that extra point, that one point compactification, that also becomes naturally a Riemann surface, and this map then, the extended map then becomes an isomorphism, and then we call the corresponding curve as the projective algebraic elliptic curve associated to tau, to that torus, and the fact is that that curve will actually live in projective 2 space, so that will require me to explain to you how what projective 2 space is. Okay, so anyway, so let us get along with what we need to do in this lecture, namely to show that Z2 sub tau E2 sub tau is naturally a Riemann surface. Okay, so we shall show E2 sub tau is naturally a Riemann surface so that phi sub 2 is biholomorphic. So, so the point is that somehow more generally the question is that if you give me an algebraic equation like this in 2 variables, then I can look at the set of zeros of that equation, okay. That will be the set of zeros will be a subset of C2, and the question is under what circumstances can I naturally make it into a Riemann surface. So this will be done using the implicit function theorem for complex variables, along with the fact that the graph of a holomorphic function is automatically a Riemann surface. So that is the starting point, okay. So what we will do is what I will do is we first show that the graph of a holomorphic function is naturally a Riemann surface. The point is that once you prove that the graph of a holomorphic function is naturally a Riemann surface, then what you can do is that, you know, given a polynomial equation in 2 variables like this, given a 2 variable polynomial, you know, I can, using the implicit function theorem, I can locally get an explicit function of the second variable in terms of the first variable, and then the fact is that and in fact the implicit function theorem will tell you that locally this will look like a graph, and since locally since every graph is already a Riemann surface, so you will get on the zero locus of a polynomial like this locally a Riemann surface structure, and then you will have to show that there is compatibility between the charts, and once you do that you get a globally a Riemann surface structure on this, okay. But this will not happen for any polynomial. The polynomial has to satisfy certain hypotheses of so-called hypothesis of non-singularity, which are the hypotheses that are needed for the implicit function theorem, okay, which I will make clear. And so start with G from V to C, where holomorphic or that is analytic, complex analytic, and V is an open subset of the complex plane. So you look at a function G defined on an open subset V of the complex plane, okay, and taking complex values, right. What is the graph of G? The graph of G is, well, it is the set of all points Z comma GZ where Z belongs to V. This is the graph of this function. The graph is a subset of V cross C, okay. So pictorially, though you know, it's hard to visualize the graph of a complex valued function of a complex variable, because essentially it will be 4 real dimensions, okay, but nevertheless we do it in a very suggestive kind of way. We map we put V here, or rather we put C here, and we put C here and think of this as C2, okay, and then we think of V, the open set, as a patch here, and then, you know, we draw the graph. So this is just like you would draw the graph of a real valued function in the first quadrant if it has positive values. So, you know, so you end up drawing something like this, and every point, so given a point Z here, then I get this point, which is this point is Z comma GZ, and this, so this projects down to Z and to Z, and that projects down to GZ, okay. So this is a subset of you can see it's a subset of C cross C, alright, and the point is, how do you make this graph naturally into holomorphic, I mean how do you make it naturally into a Riemann surface? see the fact is that you need a homeomorphism of this graph with an open subset of the complex plane, and that is obviously given by the first projection. Okay, so what you do is this is what you do, you consider P2 I mean rather P1 from C cross C to C, that will just send any lambda comma mu to lambda. This is the first projection. Okay, and then what you do is you restrict this first projection to the graph, of G, that will go from the graph of G to V. Okay, so now what you will have to notice is that this is actually a homeomorphism. In fact this is you can see that you can see obviously that so you are just sending z comma gz back to z. Okay, and it is obviously surjective because given any z I have the corresponding point on the graph z comma gz and whose image will go back to z, so it is surjective, and it is obviously injective because if z1 comma gz1 and z2 comma gz2 go to the same z1 equal to z2, so then if z1 equal to z2 then gz1 equal to gz2 trivially, therefore this is a bijective map. Okay, and also this map has an inverse, namely you just send has inverse from V to graph of G. This is a natural map, you just send z to z comma gz. This is the inverse map. So let me call this inverse as phi. Let me call this as phi sub G. Okay, so if I take V comma phi sub G, I should rather take yes, so I should take so if I take graph of G comma phi sub G is a chart, it is a global chart on it is a global chart for graph G. Okay, and in fact this is since there is only one chart. Okay, since there is only one chart, there is no compatibility to be checked, therefore this makes the graph of G into a Riemann surface. You have just identified graph of G with V, which is the domain of the function G. Alright, and so this single chart will do to convert it into a Riemann surface. And of course there are other little points for a Riemann surface. First of all, the topological space needs to be, if you insist you want it to be connected, then you had better assume that V is a connected subset. Even if not, then you will be able to break down V into connected components, and each component will be converted into a Riemann surface. Then the other thing is you also want it to be Hausdorff and second countable, which is obvious because you see because of this homeomorphism, graph G is homeomorphic to V, and a subset of the complex plane is of course Hausdorff and second countable. Okay, so if you stick by the definition that a Riemann surface structure is a complex atlas, okay, a system that is a system of coordinate charts which are compatible with each other on a manifold which is Hausdorff second countable and connected, then all these conditions are satisfied. Of course connectedness you will have to assume for V. Okay, so in any case this is the way in which you can make the graph of a function into a Riemann surface, and then now so once we do this for the graph of a holomorphic function, then we can go down and do it for a function of two variables. Okay, so I'll state the implicit function theorem. This is exactly This is exactly the complex analog of the implicit function theorem that you would have in real variables, and the philosophy of the proof is perhaps nearly the same. So let f of small f of x comma y be a polynomial with complex coefficients okay, and of course when I write x comma y, you must always beware x and y are complex variables, they are not real variables. Okay, probably it would have been better if I use z and w, but never mind. Please remember that capital X and capital Y are complex variables. Okay, we are already in the complex setup, so our scalars are always complex numbers. Okay, so let z of f of x comma y be the 0 locus of f of x comma y in C2. Okay, look at the 0 locus. Okay, so coming back to think of it, it's good that I didn't use z and w, because now I want z to denote the set of zeros. So that is, what does it mean? It means z of f of x comma y is the set of all lambda comma mu in C2 such that f of lambda comma mu is 0. This is the 0 locus, and the point is the implicit function theorem says that you can solve the equation f of x comma y equal to 0 can be solved locally as y is equal to g of x locally, provided there is a condition on the derivative, just as in the real implicit function theorem. So let me say this, let lambda comma mu be a point in the 0 locus such that if I differentiate partially f with respect to y, the second variable, and evaluate it at lambda comma mu, the resulting value is non-zero. Okay, so basically if you what is the implicit function theorem? It says that if you are trying to solve f of x comma y equal to 0, which is an implicit relationship between x and y, then you can solve for it as y is equal to gx at a point where the partial derivative of f with respect to y does not vanish. This is the implicit function theorem. Okay, so that's the condition that I have put here. All right, so what it says is, so let me write that. Then there exists an open neighborhood. U lambda, or let me call it as v lambda of lambda in C, and a holomorphic map G from v lambda to C such that the following things happen. The first thing is G solves f of x comma y for all x in v lambda. Okay, so let me write that G y is equal to gx solves f of x comma y equal to 0 for all x in v lambda. Okay, that is for every lambda prime in v lambda, f of lambda prime comma g lambda prime is 0. This is the implicit equation is solved by an explicit equation in a neighborhood of the variable in the neighborhood of the point where the partial derivative with respect to the explicit dependent variable is non-zero. Okay, the second condition is, of course, what will happen is that and g is holomorphic, so what's its derivative? The derivative can be dg by dx is actually minus dou f by dou x divided by dou f by dou y. This is the derivative in v lambda. Okay, this is the so this is an identity that you get, that you take the total derivative of this. Okay, if you take the total derivative of this and treat y as a function of x, then you'll automatically get this. But then to bring it to this form, you must have that the derivative dou f by dou y is non-zero. So you must remember that f is small f is a polynomial, so dou f by dou y is also a polynomial, it's always continuous, and if and if a continuous function doesn't vanish at a point, you can always choose a neighborhood where it's never going to vanish. Okay, so this is what that's what allows me to divide by dou f by dou y. Okay, and the third thing is the most important. Z, the zero set of f of x comma y locally at the point lambda comma mu looks like the graph of G. Okay, so in other words, so the first point is for every lambda prime v lambda, we have f of lambda prime comma g lambda prime is 0. That's one thing. The other thing is because lambda, if you take a point lambda prime comma mu prime in the zero set of fxy, then it must happen that mu prime is actually g of lambda prime. That is what it says. Okay, so in other words, if I take, so let me draw a diagram to explain this more graphically. So you see, you have, this is C2, C cross C, and what is happening is that you have this zero set of f of x comma y. Okay, and then you are choosing a point lambda comma mu with the property that the first partial derivative of small f with respect to y at that point does not vanish. Okay, then what happens is that you are able to, so then you project down here, you get this point lambda, and then you are able to find a v lambda. V lambda is a open neighborhood of lambda, and on v lambda there is a holomorphic map. If you draw the graph of this map, namely you take the set of all lambda prime comma g lambda prime here, then that is exactly this graph. So if I just extend it like this, and if I extend this like this, then this guy is exactly graph of G. Okay, so in particular it means that if you take any if you take any lambda prime comma mu prime such that lambda prime is in v lambda, then mu prime has to be g of lambda prime. Okay, so there is so it's locally the graph of that function. Okay, and if you grant, I'm not going to go into giving a proof of this because it is quite standard and you can look it up, but the point is that I want to say that once you have the implicit function theorem, the immediate corollary is that if you give me if you look at the zero set of a polynomial, then locally already it is a graph of a holomorphic function, therefore locally it is already a Riemann surface, because we have already I have already explained to you how very easily the graph of a holomorphic function is a Riemann surface. So what is the upshot of this result is that the moment a polynomial satisfies this condition, okay, then in a neighborhood of that point it's a Riemann surface. You can make a neighborhood of that point on the 0 locus Riemann surface. The question is what happens if it does not satisfy this condition. Then it might satisfy the same condition, similar condition with respect to the first variable, okay, and then you can use projection onto the second variable, and instead of writing y as a function of x, you will be able to write as x as a function of y if dou f by dou x at a given point is non-zero, okay. So all these put together, the point is that if you have a polynomial which is so called non-singular, namely which satisfies the condition that one of the partial derivatives of the polynomial never vanishes at each point, okay, then it is very clear that the graph, the set of zeros of that polynomial is naturally locally a Riemann surface, okay, and the only thing that one has to check that it is globally a Riemann surface is to check that all these local Riemann surface structures agree. You will have to just check that all these charts that you got by the graph construction, they are all compatible. Once you check that, then it is very clear that the zero set will be a Riemann surface, okay. So and of course the zero set being it's a closed subset of C2, so it's automatically Hausdorff and second countable, okay. Any subspace of a Hausdorff space is Hausdorff, and any subspace of a second countable space is second countable, so those conditions are automatic. Of course you might want it to be connected, and the fact is that you'll so if you put this non-singularity condition, then it automatically means that it's connected, and in fact more generally you could have assumed that or rather to be on the safer side, one sufficient condition you can put on f is that it is irreducible as a polynomial, okay. So that is a technicality that one need not worry about at this stage, but at the worst, if you take a polynomial whose first partial derivatives simultaneously do not vanish at any given point, then it becomes a Riemann surface, okay. So let me write the rest of it. So if dou f by dou x at lambda comma mu is not equal to 0, then there exists an open neighborhood w mu of mu in C and a holomorphic function h from w mu to C such that z of f of x comma y is locally for x in for y in w mu the graph of h. So this is the condition on the other variable, okay. So so that is the so you have to rewrite. I'm not writing everything down, okay. I'm just stating the case when the first partial with respect to the first variable is non-zero, okay. That was the case when the first partial with respect to the second variable is not zero, right. Then you can write the second variable as a function of the first variable. In this case you will be able to write the first function, first variable x as a function of the second variable, so x will be h of y, okay, right. So yeah, so what is the upshot of this? The upshot of this is that if you give me a polynomial which satisfies one of these two conditions at each point of its zero locus, then there are Riemann surface structures locally, okay, which come out of the graph construction, okay. So let me write that down. Thus, if a polynomial fxy is such that there is no point, there is no solution to the system f of x comma y equal to 0, dou f by dou x at x comma y is equal to 0, dou f by dou y at x comma y is equal to 0, in which case we say f is non-singular. Okay, then the 0 set of f of x comma y is locally a Riemann surface. Okay, so the upshot of the thing is that the 0 set of this polynomial, which is non-singular polynomial, non-singularity means that you should not be able to find a point on the 0 locus at which both first partial derivatives vanish. Okay, then f is such a polynomial is called non-singular, and then the 0 locus is locally Riemann surface. Now I only need to verify that it's a Riemann surface. I have to only tell you that all these Riemann surface structures locally, they all glue together, I mean that they all agree. Namely, I just what do I mean by saying it is locally a Riemann surface? Locally I am getting charts which are given by the projections of, because locally these are graphs of holomorphic functions, and then I take projections onto the independent variable, then I get the charts. So to show that all these together make this into a Riemann surface, I will have to only check that the charts are all compatible. Okay, so if I do that, then for a non-singular polynomial I will have that it's automatically a Riemann surface. Okay, then you know what I'm going to do, I'm going to check that this particular polynomial that I'm having, this cubic, satisfies I mean this polynomial here, I'm going to show that this satisfies the non-singularity hypothesis, and therefore that will tell you that this E2 tau is in fact a Riemann surface. Alright, so and we will also see the way in which we have done it. We will also see that this map is naturally holomorphic, because what will actually happen is that locally the coordinate charts are just given by projections, and the first projection is going to be phi, which is holomorphic, the second projection is going to be phi prime, which is holomorphic, therefore this map becomes holomorphic. It is a holomorphic bijective map, so it is a holomorphic isomorphism, and we are done. Okay, so so let me go ahead and try to show you why all these Riemann surface structures locally, they all give the same Riemann surface structure on globally. Okay, so we verify that all these Riemann surface structures glue, that is agree, that is the charts given by the graph construction, the local charts given by the graph construction are mutually compatible. So basically there are three cases. The first case is when the local Riemann surface structures comes from both projections are on the first variable. Okay, basically I will have to take two local Riemann surface structures, okay, and show that at the intersection the charts, the transition functions are holomorphic. That is what I have to show. So it might happen that the Riemann surface structures on these two overlapping pieces, open pieces of the 0 locus, they both come from the first projection, or they both come from the second projection, or one may come from the first projection and the other may come this from the second projection. So there are three cases. So let me draw diagrams for each of these. So so this is the first case, namely so here is my this is my zero locus, and well basically I have a point here. Let me call this as P1. Oh god, no, let me call this as something, let me call this as T1, let me call this as T2, okay, and so T1 is lambda 1 comma mu 1, and dou f by dou y at T1 is not 0. So what happens is that you find a neighborhood lambda of lambda 1 in C, which is given by v sub lambda 1, and you find a function g1, a holomorphic function from g1 to C, such that the graph so z of f x comma y is equal to graph of g1 for x in v sub lambda 1, okay. So so in this case, so basically if I draw a diagram, it's going to look like this. So here is my, so this is my v1, v sub lambda 1, okay. Then similarly let me assume that so this portion that I have drawn here, so from here to here the z of x comma y is the graph of g1, okay, and then you also have the same conditions for T2, okay. So dou f, so T2 is again lambda 2 comma mu 2, and dou f by dou y at T2 is non-zero. Then you get an open neighborhood v sub lambda 2 of lambda 2 and a function g2, holomorphic function g2 defined on that with values in C, such that z of f of x comma y is actually graph of g2 for x in v lambda 2, okay. So what happens is that, so this v lambda 2, so this is v lambda 1, and well v lambda 2 could be something like this. So let me not draw it here. So here is v lambda 2. So this is lambda 2. So this projection is lambda 2. Okay. So from here to here, this is v sub lambda 2. All right. And so what are the so how do I check that these two charts are compatible? So you see, basically I have this open set, which is the image of v lambda 1, okay, and then I have this open set, which is the image of the holomorphic of v lambda 2 under the holomorphic map, and this is the intersection. So this intersection, I can call this intersecting set as W12, rather let me call this as U12, okay. And so what is the situation? So the situation is I have to look at the transition functions. So I have from U12, on the one hand I have, so there is something that I have to correct here. See when I write a chart, okay, the first member is an open set on the topological space on which I want to get a complex coordinate. The second one should be defined on that. So actually this should not be phi sub g, this should actually be P1, okay. So please correct this, this should be P1. So that is the global chart. So you see, so you know, so I have P1, that is one P1 which goes from U12. U12 is thought of as sitting inside, well, you know, if I call this whole thing as U1, okay, and if I call this whole open set as U2, okay. So this is, if I think of it as sitting inside U1, then my and u1 is actually graph of g1, this u1 is actually graph of g1, u1 is actually graph of g1, and this is from u1 it will go to v sub lambda 1. Okay, this is just p1, and this is a holomorphic isomorphism, this is a homeomorphism. Okay, and so I will go into p1 of u12. So this is the which sits inside this. Okay, so it will be this region here, I mean it will be this open set. Okay, and you also have the coordinate coming from u2 via g2, so you have also u2 which is graph of g2, and you have, well, again it is p1, so this is p1 which is again an isomorphism with v sub lambda 2. So this will go to p1 of u12 again. Okay, now if I follow this up, so the transition function is the composition of these two. Okay, if I do that, I get the identity map. See, because if I start with a lambda, so transition function, what is the transition function? The transition function will be just lambda going to from here to here, you will go to lambda comma g1 of lambda. Okay, you will go to lambda comma g1 of lambda, but then you see the and then if you project it again to the first variable, I will simply get lambda. So you can see that the transition function is just the identity map, it is just the identity map on this intersection. Okay, and the fact that these two open sets v lambda 1 v lambda 2 intersect is because u1 and u2 intersect, and I am actually trying to check the compatibility on u12, which is the intersection of u1 and u2. Okay, so the transition function is just identity, it is just the identity map, hence holomorphic. Okay, so this settles the case that the local charts that you get are compatible when both are graphs of functions of the first variable. Okay, as you can, I won't be writing it down, but if I do it with the assumption that both partial derivatives with respect to x are not vanishing. Okay, then I will have to take projections with respect to second variable. So effectively the argument is you just take a mirror image of this, you take a mirror image about the diagonal line, that is the kind of diagram you will get, and essentially in that case also you will see that the transition function will continue to be the identity, so it is holomorphic. Okay, so the only case that I will have to worry about is when one of the partial derivatives is with respect to x and non-vanishing, and the other is with respect to y and it is non-vanishing, and in that case you will see that it will be one of those functions whose graphs is being considered, and so it's in that case also it will also be holomorphic. Okay, so let me just write that down. So similarly we can argue for the case when dou f by dou x at lambda comma mu is non-zero, and dou f by dou x at t1, so let me use t1 t2, at t1 is not 0 and at t2 is not 0. Okay, so similarly you can argue for the other case, in which case also the transition function turns out to be identity, so it is holomorphic. So the only case that is left is that when one of these is with respect to x and the other is with respect to y, which is also pretty easy. I will write it down. we are left with compatibility checking for dou f by dou x. Let me write dou f by dou y at t1 is not 0 and dou f by dou x at t2 is not 0. So this is the only case you have to check. Okay, that means the charts are coming from different projections on different variables. Okay, so in that case, if I try to draw the same kind of diagram, what I'll get, you can see it's pretty easy. So you see this is my 0 set of f of x comma y, and so I have this. So here is my t1, and here is so this is my, so I get this. This is my v sub lambda 1. Okay, and then and this portion is u1, and u1 is just the graph of g1, where g1 has been defined as a holomorphic map from v lambda 1 to c. Okay, and then you also have t2 here, but with respect to t2 it's only the first variable partial derivative which is non-zero. So you have basically you know, something like this. So I get an open neighborhood of this projection of t2 which is mu2, and I get a w sub mu2 which is an open neighborhood of mu2. Okay, this is of course open neighborhood of lambda 2. Okay, and this portion is u2, and u2 is actually the graph of h2, where h2 is from w mu2 to c. Okay, this is lambda 1, sorry, this is lambda 1, thank you. Yeah, this is lambda 1. So so then you see, if I look at this piece which is u12, okay, and I try to look at the transition function, it's pretty easy. See, what you will get is that if I write the same kind of diagram as here, so u12 is sitting inside u1, and u1 is from, and then you have first projection of u1 into v sub lambda 1. This is a holomorphic isomorphism, and under this projection you are looking at p1 of u12, which is going to be a open subset of is going to be an open subset of v lambda 1, and this is also of course homeomorphic, and then from u12 you also have u12 is also sitting inside u2, and from u2 it's p2, it's the second projection because the coordinate chart is in this direction. Okay, so it's p2 and this goes to w sub mu2, and so this second projection will give me this is p2, so it's p2 of u12, which is an open subset of w mu2. And now if I look at the transition function is if I start with a lambda, it will go to lambda comma g1 of lambda. Okay, and then if I take the second projection, it will go on to g1 of lambda. The composition is therefore lambda going to j1 lambda, which is holomorphic by definition. Therefore the transition function is holomorphic. So you are done with this case also. So which is holomorphic. So this implies that the moment you take a polynomial fxy which is non-singular, then the zero set of that polynomial is automatically a Riemann surface. Okay, so let me write that down. Thus if f of x comma y is non-singular, its 0 set z f x y as a subset of C2 is naturally a Riemann surface. So, it is naturally a Riemann surface. Now, I will verify, I just want to say that this E2 tau, I want to say E is actually a Riemann surface. The only thing I have to verify is that this polynomial capital F2 sub tau is non-singular. So, so to ensure that F2 tau E2 tau, which is just the 0 set of F2 tau, is a Riemann surface. We need to only check that capital F2 sub tau is non-singular. So, that is there are no there are no solutions to the system F2 tau of x comma y is equal to 0, dou F2 tau by dou x is equal to 0, dou F2 tau by dou y is equal to 0. Okay. So, let us write this out, it is pretty easy, and you will see that we will be using again the fact that E1, E2, E3 are distinct. Okay, E1 tau, E2 tau and E3 tau, which are the zeros of the derivative of the phi function, you know, they are the 3 distinct zeros of the phi function, and their distinctness is what is going to give you the non-singularity in this case. Okay, you will see, we will see that. So, let us do the computation. So, what you will get is basically, so I will get let lambda comma mu be a solution, okay, and we let us assume there is a solution, get a contradiction. Okay, let lambda comma mu be a solution and we arrive at a contradiction. So, what it will mean is lambda comma mu satisfies that equation. So, I will get 4 lambda cube minus g lambda cube minus g2 tau lambda minus g3 tau minus mu squared is 0. This is the first equation. The second equation is I differentiate dou f2 tau by dou x, and this is if I differentiate it with respect to x, I am going to get 12x squared minus g2 tau, that is all. Then if I so this equal to 0 at lambda comma mu will tell me that 12 lambda squared minus g2 tau is 0, okay, and then dou f2 tau by dou y is 0. For that condition I differentiate partially with respect to y and I end up with minus 2y. So, the condition I will get is minus 2 mu is 0, alright, and this will already tell you that mu is 0. Okay. So, you will get so the first thing I want to tell you is that you see if So let me go back to the first equation, put mu equal to 0. So I will get 4 lambda cube minus g2 tau lambda minus g3 tau is 0, okay. So I will get this and then I will add this equation also, 12 lambda squared is equal to g2 tau, okay. So I will get these 3 equations, okay, and I am just saying that these 3 equations will give us a contradiction. See, first thing I want to tell you is that you know so let me so as I told you, the point comes from the fact that when you factorize the right side of this equation into 3 linear factors, the zeros are e1 tau, e2 tau, e3 tau. They are the values of phi tau at half, tau by 2 and 1 plus tau by 2, the 3 fundamental zeros of the derivative of the phe-function. They are distinct, we have already seen that. So if you use that factorization, you will actually what happens is that the 4 lambda cube minus g2 tau lambda minus g3 tau, this factorizes as 4 times lambda minus e1 tau into lambda minus e2 tau into lambda minus e3 tau, okay. And then if you now calculate the so called discriminant of this cubic, discriminant of a polynomial equation of one variable is just the square of the difference of the distinct of its roots, okay, square of the difference of its roots taken in some order, okay. And it is an important tool in algebra, because you can check that a polynomial has distinct roots, namely that it is so called separable, by checking that the discriminant is non-zero, okay. So if you calculate the discriminant in this case, this is a little bit of algebra which you should be able to do, then you will find that it's not a difficult exercise, you can do it. Then you will find that if I take the discriminant is just product over I less than j ei tau minus ej tau. These are the square of the differences, okay, and you can check that this discriminant, you compute it, you can see that this discriminant, when you compute it, it turns out to be let me write it, tell you what it is. It is 16 times g3 tau, 16 times g3 tau, I think squared minus no, cube minus 27 g2 tau the whole squared. So this is the discriminant, and the discriminant is not equal to 0. The discriminant is not 0. So the discriminant is not 0 because all the ei's are distinct, okay. And so you see, already mu is 0. If lambda is 0, okay, if lambda is 0, what will tell you? It will tell you that g2 and g3 are 0. If g2 and g3 are 0, then the discriminant is 0. That's a contradiction. So the first thing you can conclude from this is lambda is not 0. So you see, lambda is not equal to 0, okay. So and it also, and once lambda is not 0, it's also clear that g2 is not 0 and g3 is also not 0, okay. So which implies that g2 tau is not 0, g3 tau is not 0, these two are not 0, okay. And then what I can do is literally I can just eliminate lambda from these equations, and so I have 12 lambda squared is g2 tau, okay, and I have so I eliminate lambda from these two, okay, and believe it or not, you eliminate lambda from these two, what you will get is g3 cube tau minus 27 g2 squared tau equal to 0, okay. It will give you if you eliminate lambda, you will exactly get determinant is 0, which is not true. That's the contradiction, okay. So eliminating, so basically I take a square root of lambda here and equate it to a cube root of lambda from here, and then I raise both sides to the power 6, and that's it. So eliminating lambda gives 27, I mean you will get G3 cube tau, wait a minute, I think it's G2 cube and G3 squared, so I should be careful. So this is G2 cube and this is G3 squared. Let me check that. Yeah, it is G2 cubed and this is G3 squared, please correct it. So eliminating will give you G3 squared minus 27, G2 cube minus 27 G3 squared tau is 0, a contradiction. So you see it is the distinctness of the zeros of the derivative of the phi function that actually gives you the fact that the corresponding polynomial that defines the affine algebraic elliptic curve is a non-singular polynomial, therefore it becomes a Riemann surface. And then so the moral of the story is that this E2 tau, this elliptic curve, is indeed a Riemann surface naturally by the construction that we have just seen using the graph construction, the implicit function theorem. And then now so E2 tau is a Riemann surface, and the bijective continuous map that I wrote down, namely phi2, it is from the torus minus the special point which is the image of the lattice to the to E2 tau is basically this map is Z going to, well, so it's just Z. So I put a box here to show that this is the equivalence class because this torus is a set of equivalence classes, and this goes to phi Z, phi tau of Z, phi prime tau of Z. This map is actually holomorphic because if you project onto the first variable it gives the holomorphic map phi sub tau, and if you project on the second variable you get the holomorphic map phi prime sub tau is holomorphic. Hence an isomorphism, hence biholomorphic. Okay, so you because essentially how do I check that this is holomorphic? The method is that I will have to take locally an open set which has a chart, so locally it will be a graph, and then for a graph the coordinate map is just projection onto either the first variable or the second variable. So I will be essentially locally getting p tau or p prime tau depending on whether I am projecting on the first variable or on the second variable, therefore they are holomorphic, therefore this map is a holomorphic map. Okay, and that shows you that the punctured torus is naturally isomorphic as Riemann surface to the affine elliptic algebraic curve defined by the polynomial equation that comes out of the differential equation satisfied by the Weierstrass phi function. Okay, so I will stop here. The next lecture I am going to tell you how you can extend this map from the torus to a one-point compactification of this affine elliptic curve, which will live in projective 2 space. Okay, so I will stop here.